All right, so we're going to talk now about fundamental subspaces. Okay, so the idea is that we're going to look at trying to solve operator equations. And when I say operator equations, I mean equations of the form, y is equal to ax. And where, a is an operator. Okay, so this is the basic setup. A is going to map Hilbert space H1 onto Hilbert space H2, and H1 and H2 are Hilbert spaces. We also assume that that A is bounded. Okay, so A is bounded. It's a linear operator. It maps from one Hilbert space to another. Then remember, we already saw that that A star is the adjoint operator, and it's going to go in the opposite direction. So A is going to map from H1 to H2, but A star is going to map from H2 back to H1. Okay, now we will see in the next few slides that it turns out that the range, I'm using this telephone, I call this the telephone pole diagram, telephone pole diagram. I think this is for me, it seems to be a natural way of understanding the basic picture here. So our Hilbert space H1 is represented by this telephone pole, and H2 is represented by this telephone pole. And it turns out that, for example, H2 can be completely decomposed into two disjoint subspaces. One is the range space of our linear operator A, and the second is the null space of the adjoint of A. And these two spaces are disjoint. So this symbol here means disjoint, meaning the only element that is in both of them is the zero element. It also means that anything in the range space of A is orthogonal to the null space of A star. So the range space of A is orthogonal to the null space of A star. Okay, and then similarly, H1 can be decomposed in terms of the null space of A, an orthogonal decomposition in terms of the null space of A and the range space of A star. So we'll prove that. We haven't shown it yet, but that's something that we'll show. And then another interesting property that will be key to solving these operator equations and is represented by this dotted line here. See, these lines represent that A maps over here to the range space of A. Okay, and then A star maps here to the range space of A star. So that's what I mean by these diagonal lines. And this this sort of horizontal line that is flat represents the fact that the dimensions of these two range spaces are exactly the same. So this is something that we'll show, but the dimension of the range space of A is equal to the dimension of the range space of A star. And this is important because, we saw that there are some cases, like, for example, with differential equations, where you have a differential equation that maps Rn onto a function space, an infinite dimensional space. But it turns out, and then we can find the adjoint, which maps an infinite dimensional space onto Rn. It turns out that the dimension of the range spaces are exactly the same. So that means the dimension of the range space of that differential operator has to be finite. Okay, so this, and that leads to lots of interesting applications. Okay, so next slide, we're gonna, I just want to summarize. These are all the statements that basically we can make from that diagram. First of all, that the H1 is decomposed, an orthogonal decomposition between the null space of A and the range space of A star. H2 is an orthogonal decomposition between the null space of A star and the range space of A. And by the way, this means that anything in H1 So in other words, if I can write y in H1, then I can write y is equal to yn plus yr, where, yn is in the null space of A, and yr is in the range space of A star. And this is a unique decomposition. I can always do this. So that's part of what this means in orthogonal decomposition. And then we can say, furthermore, that the dimension of H1 is going to be equal to the dimension of the null space of A plus the dimension of the range space of A star. And similarly, the dimension of H2 is going to be the dimension of the null space of A star and the dimension of the range space of A. And furthermore, as we said, the dimension of the range space of A is equal to the dimension of the range space of A star. So these are the things that we're going to prove in the next number of slides. Okay, so before we do that, let's look at what this picture looks like for matrices. For matrices, we have, it looks similar. So the matrix A maps complex n space to complex m space. And so A star, remember, is going to be the Hermitian of A, and it goes in the opposite direction. So A maps in this direction, AH maps in that direction. And then we can decompose this, the CM that we're mapping over to into an orthogonal decomposition on the range of A and the null space of AH. And similar, Cn can be represented as an orthogonal decomposition of the range space of AH and the null space of A. And then we can say, furthermore, that the dimension of the range space of A is equal to the dimension of the range space of AH. And in fact, we'll see, we haven't defined rank yet, but we'll see another way of saying this is that the rank of A is equal to the rank of AH. We'll talk about that a little bit later. Okay, so we're going to start now proving some of these statements. So this is theorem